I spent some time in previous videos discussing heat changes for physical processes. There is a second way that the system can exchange energy with its surroundings, and that's through work. We've seen that we can calculate the heat based on the temperature change. We will see now that work can be calculated based on the volume change for a chemical process. Energy is exchanged between the system and the surroundings through heat and work. The change in energy, the total change in energy of the system, is defined as the sum of the heat transferred, represented by Q, and the work done, which is W. Change in energy is a state function. A state function is a property of a system that depends only on the initial and the final conditions, not on the process by which it happened. Here's an analogy. There's probably several sets of roads and turns you could choose to drive from home to school each morning. There's one way that's the shortest and the fastest, but there's plenty of winding, out-of-the-way paths you could drive too. No matter which path you choose, the end result is the same. You are at school. However, the number of miles you put on your car, the amount of gas you use, these properties do depend on the path that you take. These are not state functions. The change in internal energy of a system depends only on the amount of energy in the system at the beginning and at the end. It does not depend on the process by which the change occurred. The change in energy is a state function. For any state function, you can calculate the change in that property by subtracting the final and the initial values. So change in energy is the final energy minus the initial energy. Temperature is another example of a state function. We saw in another video earlier that we can calculate change in temperature in this way, final temperature minus initial temperature. Q and W, heat and work, are not state functions. Their values depend on the process involved. Let's look at two different scenarios in which a gas is contained in a piston cylinder apparatus. In the first scenario, the piston is held in place by stops. In the second scenario, the stops have been removed and the piston is free to move up and down. In both scenarios, a hot brick is placed in contact with the bottom of the cylinder. The gas is the system, the hot brick and the piston cylinder container are the surroundings. What kind of energy transfer occurs in each scenario? In the first scenario, since the piston cannot move, the gas cannot do any work on its surroundings. Remember, work is defined as a force acting through a distance. If the piston is held in place, the gas cannot move it. No work can be done by the gas on the surroundings. All of the energy transfer here is as heat. All of the energy transferred from the brick went into increasing the temperature of the gas. When you measure Q, the heat change of the system, at constant volume, the measured heat change is equal to the total energy change of the system. In the second scenario, though, energy can transfer as heat and as work, because this time the piston can move. Work is equal to a force acting over a distance. In our piston cylinder apparatus, the force is related to the pressure the gas applies to the underside of the piston, the surface area of the piston. The distance traveled is the change in the height of the gas in the cylinder. Area times change in height is the same thing as the change in volume of the gas, making work equal to the pressure of the gas times the change in volume of the gas. When the gas expands, the change in volume is positive and the system is doing work on the surroundings. Work done by the system on the surroundings should be negative. So an increase in volume, a positive delta V, results in a negative sign for work. This equation is usually written with work as a positive value. That gives us the equation work equals negative P delta V. Looking back to our original drawings, we see that this time not all the transferred energy went into increasing the temperature of the gas. Not all of the energy was transferred as heat like in the previous scenario. This time, some of the energy is transferred as heat, but some of the energy is used as work. The measured value of Q is not the same as the total energy change of the system. Some of the energy is used up as work. Some of the energy caused an expansion of the gas. Comparing these two setups, if the same amount of energy is added to the gas in both systems, the gas in the first setup will be warmer than the gas in the second setup. Some of the energy in the second setup transferred as work, not heat. In this first scenario, the reaction was forced to occur at constant volume. In the second scenario, since the piston could move, the volume of the system could change. As the temperature of the sample increased, the volume increased, pressure stayed constant. Most experiments performed in a lab are more like the second scenario described here. When we do experiments in the classroom, they're done in open containers at constant pressure, that constant pressure being the current atmospheric pressure. If we do an experiment that causes an expansion of the system does work against atmospheric pressure while expanding. Not all the energy is converted to heat. Some of the total energy is used up as work. The difference between our experiments and this piston cylinder apparatus is that our reactions aren't occurring in a container with a piston whose movement is easily measurable. So it's difficult, if not impossible, to measure the work done by the system. So for most chemical processes, it is often better and definitely easier to refer to a quantity that is related to the total energy change, delta E, but is not exactly the same thing. Instead of referring to delta E, we refer to delta H, the enthalpy of the system. Enthalpy is defined as the change in heat of a process that occurred at constant external pressure. When we measure the heat change in our labs, when we measure Q, it's equal to the enthalpy change for that reaction. Delta H is not exactly the same thing as delta E, but delta H focuses on what chemists are most interested in studying in a chemical reaction. We will study enthalpy more in our next unit. For now, at least, understand that there is a difference between change in internal energy and change in enthalpy.